Well, good morning, everybody, and I guess welcome to the end of the road in terms of at least our class meetings. So just a reminder that we won't meet next week either on Tuesday or Thursday. The idea is next week is available for you to finish up any outstanding assignments, work on your project, et cetera, et cetera. So just a reminder, there is a quiz next Friday on Chapter 6, so the material we're going to finish today. I'll definitely stay in touch with various email announcements and so on. And if you want to meet or get in touch with me in any way, that's totally fine as well. We can arrange that. We can either meet on Collaborate or Zoom, or even if you want to meet in person, that's fine too. If you want to discuss anything related to the project or otherwise. So we'll kind of just wrap things up. I haven't changed anything on the Moodle page yet. I will do that soon, but just in light of what we discussed last week, I mentioned that I'm happy to push the project due date back. We'll probably, what I'll do is I'll say tentatively do Monday. If for some reason you're not done there, I can probably push it maybe one more day or into, I do have to watch out for when final grades are due, obviously, and I need probably at least a day to grade everything. But since I have all my exams the previous Friday, I'll have plenty to occupy myself over the weekend. So no need to rush getting those done. So I'll make that change on the page at some point and then just kind of send out a formal announcement. And I am behind, I know, on getting things graded and giving feedback, and I will do that soon. Other than on the quizzes, at least those are caught up. And you should be able to review quiz 5 if you want to take a look at that. So let me know if you have any questions about anything, or there's anything you want me to go over with you. Happy to do so. So in the meantime, let's wrap up Chapter 14 and the course material. So talk a bit more about support vector machines. Okay, so last time we saw the idea behind a support vector machine is to essentially expand the feature space into some much larger space using this thing called a kernel function to implement essentially an augmentation of the feature space where you don't actually have to, define the new features. You just simply look at these dot products, so inner products between the feature, the existing features, and that gives you all the information you need. Okay, and so we saw at the end a conclusion of showing that support vector machines work very well on certain kinds of nonlinear problems, and we used the example of what we call the two spirals problem. Okay, so overall, support vector machines, as we've looked at them so far, these are a mathematical machine learning approach to, as we've emphasized a few times, binary classification problems. Okay, so everything we've looked at, all the examples we've seen, involve separating two classes. So you have and in the cases where we've been able to graph them, we've graphed them in the feature space, and the idea is that we graph the features, but then the different classes are indicated by, say, different colors or different shapes or both. But that's the idea. We're looking at a binary classification problem in the target variable. Okay, but we can actually extend this. So we can extend this idea to, so we can extend it to multinomial classification. And we can also extend it to regression. All right, so multinomial classification is in some sense the easier one to approach because it's still a classification problem. Regression's a little trickier, but we'll see how to do it a little later. Okay, so let's start with more than two classes. All right, so there are two general approaches to doing multinomial classification. We have support vector machines. The first is what's called one versus all. or OBA. Okay. And so the idea is we fit a support vector machine to each class. Okay. And what we mean by that is even though we have multiple classes, we think about there as being whatever class we care about and then everything else. Everything. So in other words, we reduce to a binary problem. So we do binary classification with whatever class we care about, say class J. Separating, say class J, whatever class we care about, from what we'll call class not J. Okay. So in other words, we group all the other classes together into a single class, just simply everything else, right? So everything that's not in class J. Okay. And then what we do, so we do this for each of the classes. We create this support vector machine. And then we classify to the class for which the resulting, the corresponding margin is the largest. Okay. So what do we mean by margin here? So remember that what we're doing when we do a support vector machine is we're doing some kind of separation, good hyperplane separation in the higher dimensional space, and then projecting back down into the feature space where we get then usually like a nonlinear separation boundary. Okay. So the idea is that there's a, when we do the when we form the support vector machine, when we create the hyperplane in using the kernel trick in the higher dimensional space, that hyperplane, there's a margin associated to it. Remember that. So in this case, so here, margin refers to the minimum distance from the separating hyperplane in expanded space to the classes. Okay. And if we use just a hyperplane, if we can actually separate in the original feature space using, say, like the hard margin classifier or soft margin classifier, then the margin is just exactly what we said it was before. Okay, so that's the idea. Is you say, okay, well, what separation do we get is the best, and then you just classify into that class. Whatever class gives you the best separation, that's where your values go. That's where you make your prediction. The other option, so basically what we're doing is we're comparing one class against all the others, hence the name one versus all. The other way to do this is what's called one versus one. So abbreviated OBO. Okay. So we look at all pairs of classes. Okay. In other words, we kind of take each pair of classes and do a comparison. And how many ways are there to do that? However number of classes there are, so number of classes choose 2. Okay, if you're familiar with choose notation for combinations. So number of classes choose 2 ways to do this. So these are the number of different pairings we have to look at, which of course could get very large if your multinomial classification has a lot of classes. Okay. And then for each pair, so you take, say, class 1 compared to class 2, class 1 compared to class 3, and so on, class 2 compared to class 3, and so on. So for each pair of classes, fit a support vector machine to separate them. So we form, say, a support vector machine separating class J and class K, right? In each possible combination of J's and K's. Okay. So then if you have some target value for each pair of these classifications, or for each pair of classes, the support vector machine is going to predict that your target value, your value lands in some class, right? So you have some value you're predicting to. And so what we do is we classify to whichever class, in some sense, wins the most often. Right? So let's say we have some predicted observation that we're feeding an observation, a data point into the support vector, into the algorithm, and we want to know where to classify it to. And it classifies to say class 5 the most often of all these comparisons, class 5 versus class 1 versus class 2, etc. So then we would say, we would predict it lands in class 5. Okay. And so what we're doing in both cases is we're simply using the binary support vector machine algorithm, right? So we haven't actually had to create anything new. We're simply kind of going to use what we've already discussed and then interpret the results, right? So for both approaches, the basic, in other words, binary SVM algorithm is the mathematical approach being used. The mathematical method being used. So we're simply kind of reimagining it a bit, reinterpreting it, or as in the second case, doing it multiple times. Okay, but the actual process is just the same thing we discussed as well. All right, so that takes care of the multinomial case. It's essentially just a twist, a new spin on the binary case. What do we do for regression? Well, here it's a little harder because now we're doing a much different kind of supervised learning problem. So in this case, we'll call this support vector regression. So SVR. All right, so support vector regression extends the support vector machine approach to regression problems, as the name suggests. So there are different ways to do this. The most common form, which is the only one we'll talk about here, really, is called epsilon insensitive loss regression. Okay. So fancy name. What does that mean? So let's, to understand how this works, let's go all the way back to the beginning, so to speak, to linear regression. Okay. Just recall. So least squares regression minimizes, what's the mathematical approach behind least squares regression? It minimizes the sum of squared residuals. Okay. So given a feature value x and a target value y, the corresponding residual, let's call it r of xy, is simply y minus, say, f of x, where f is the regression algorithm. Okay. Where in particular, what is f of x? It's the regression hyperplane, right? So in this case, beta 0 plus beta 1 x1 plus ... plus beta p xp, which, as we said, if you set this say equal to 0, that gives you the equation of a hyperplane. So it's the generating function in some sense for a hyperplane equation. Okay, so in that sense, it's reasonable to see that, well, to think that this might be related to the support vector machine idea. If we're doing separation with a hyperplane and a linear regression, multiple regression equation have the same kind of idea. So, all right. So, what's a problem with least squares regression? Is so one of the things that we say, I mean, even in say like 100 level statistics, when we're talking about regression, is be careful about doing regression when you have lots of like large outliers, right? And the problem is that squaring the residuals, which is what we do, right? We take the sums of squares of the residuals, makes any outliers very influential on the fit. Okay. So if you have outliers, then they have large residuals, and then their squares are big, and so that influences the minimization in the least squares regression. Right? So what we want to do is essentially we want to introduce a way of kind of minimizing outliers. So we want to kind of introduce a fudge factor that will we're going to change our loss metric and try to blunt the impact that outliers have. Okay. So for support vector regression, a good way to deal with this is to introduce a new loss metric that is more robust to outliers. Basically, kind of intuitively, what we're trying to do here is this. Remember, like back when we were looking at the hard margin classifier, and we saw, we looked at that. We looked at what's called the GLM, and then the LDA. These are all different ways of fitting a hyperplane. So in our case, in the example, we used a line through a data set, and they all looked very good when our data set had a nice clean separation between the two classes. We did that example with purchasing a riding lawnmower based on lot size and income. Okay. But then when we introduced an outlier into that data set, they all had a hard time with it, right? They all got pulled towards the outlier, and it badly changed the equations of the lines. And in that case, the outlier, well, it was a binary classification for the target, but the same problem is going to occur if you have a numerical target, right? So now the outlier is just going to pump up the value of the loss function that we're using to measure how well the fit is, how good the fit is. Okay, so what we did in the class of the hard margin classifier is we introduced this idea called the soft margin classifier that gave us kind of some fudge factor room, right? We allowed ourselves to have a bit of overlap. So what we want to do here, in some sense, is the numerical version of that. In a way, we want to introduce a fudge factor wherein, if we're in that fudge factor, but within that, it's not going to affect our loss function too much. And the way we will do this is called epsilon insensitive loss. Okay. So what we're going to do is we're going to define the following. L sub epsilon is going to equal the max of 0 and absolute value of r of xy minus epsilon. So the the absolute value of the residual minus this number epsilon. Okay. So what does this do? Okay. So we form a margin around the regression curve. Well, regression, in this case, hyperplane, right? Of width epsilon, some positive number. Okay. Okay. So epsilon, in this case, its positive number is some threshold set in advance. Okay, so you start by you choose this number. Essentially, you're going to have like this tolerance, right? Epsilon, but it can be tuned as a hyperparameter. So you don't need to know at the start what's the best value of this to use. You can tune it if you want and figure out an optimal value for it if you so desire. Okay. So the idea is you try to contain as many data points as possible within the epsilon band margin. So the idea is we go epsilon away in both directions. So it creates a margin of width epsilon, right? With a minimal number of what we might call violations. So a violation here means the same thing as like an overlap did before with the soft margin classifier, where we allowed points to be on the wrong side, right? Now we can actually measure this because we have a numerical variable, so we have a loss function. Before it was just, did the point land on the wrong side of the decision boundary, yes or no, because it was binary classification. So there's no real way to measure how bad that happens, but now there is. Okay. So this is what it looks like. It's actually, I mean, in picture-wise, it's actually fairly intuitive what's going on. So the idea was we're creating this error band, this tolerance of epsilon around the line. And what we want is, so rather than just looking at the line, we're basically looking at this sort of this band, right? So we fudged the line by creating a band around it. Okay. All right, so what happens if a point is within the line? Well, then that L sub epsilon, that epsilon insensitive loss function is going to be 0 because the residual is going to be less than epsilon. So the absolute value part minus epsilon is going to be negative. So then the max would be 0. Okay. So going back, let me write that down. So points within the epsilon band margin have L sub epsilon equal to 0. Okay. So all such points have no effect on the regression fit. So hence the name epsilon insensitive, right? So the regression fit is insensitive to any points within epsilon of the regression hyperplane. Okay. Any points in the epsilon band. All right, and so just like with support, so like with binary support vector machines, support vector regression through the use of kernel functions to expand the space and so on, is very flexible at capturing nonlinear relationships. In this case, nonlinear relationships between in a numerical target variable. So let's look at a good example of a highly nonlinear curve and how support vector machines do a good job of it compared to some of the other methods we know. So define the following function. So call it sinc of x. And what is sinc x? It's equal to sine of x over x for x not equal to 0. And if you've taken calculus 1, you know that the limit as x approaches 0 of that function is equal to 1. So we set it equal to 1 when x is equal to 0, so the resulting function is continuous. And in fact, when you do this, you make this definition, not only is it continuous at 0, it's actually differentiable there, so it's smooth. So this is a nonlinear, highly nonlinear, in fact, as we'll see, smooth function. Okay. So what we're going to do is a spin on what we did way back when we talked about decision trees, and we looked at just a regular sine function. This function is much more nonlinear in the sense of has a derivative that changes quite a bit more, right? There's quite a bit larger variations between the minimum and maximum values of its derivative, how steep it is, in other words. Okay. Well, let's do the same thing we did back in chapter 9. So generate data, a data set using this function with some Gaussian noise, so that the points don't perfectly lie on the curve. Okay, so in other words, standard normally distributed, identically independent errors. Okay. So that's what this would. So here's a picture of what we're talking about here. So here's this sinc function with noise added to it. Okay. So the orange curve is the actual graph of the function sinc of x. So you can see it's a nice smooth function. And then our data set are all the gray points. So you can see that the points roughly follow the pattern of the curve, but with errors, right? So we've introduced some noise so that the point cloud is not exactly lying on the curve. So what we would like to see now is how well do some of our machine learning models refit a curve to this data set? Do they get close to the orange curve or not? Okay. So going back, we'll fit some models and we'll describe what we're doing, and then we'll see the results. So we fit 3 regression models to this data set. Okay. So the first is one we haven't talked about, but it's related. It's what's called MARS. So a default MARS model, so multiple adaptive regression splines. This was chapter 7. You may have seen this. If you haven't, don't worry, but it's a regression kind of type approach. Then we're going to fit a default random forest. Of course, this is chapter 11. So default meaning no tuning. As we've seen with random forest, that tends to perform pretty well. And then I'm going to fit a support vector machine model, support vector regression model, using the radial basis kernel. Remember, this is the one given by an exponential. Okay, so we set the kernel we want, and we set epsilon and we use epsilon insensitive loss as the function. But we do this with default parameters, with default tuning parameters. So we don't tune anything. We just tell it what loss function we're using, and we tell it what kernel we're using. So we have to do that. Then otherwise we leave it alone. Okay, so we're trying these three models, Mars, Random Forest, and SVR, essentially without changing much to see how well they do without tuning them to the data. Here's the results. So on the left is the result of the Mars model. In the middle is the Random Forest model, and on the right is the support vector regression model. Okay, so what can we see here? Looking at these three pictures. So Mars has two issues. One, it doesn't capture the relationship well on the left-hand side. So you can see for whatever reason, it's not fitting well to that section. There's just a flat line there where it should, of course, have a wave shape. And it has trouble with the smoothness, right? So when it transfers, it changes, say, at a local extreme point, so a local max or min, it's just a sharp change, right? So it kind of indicates we're fitting some sort of piecewise, linear, like polynomial. It doesn't transition smoothly. It makes these sharp, abrupt changes. Okay. It does a reasonable job capturing the overall pattern, other than on the left-hand side. So but the problem is it has trouble with the smoothness of the curve. Now, the Random Forest does a better job of getting the overall pattern. We see it doesn't have any issue picking up the wave shape on the left-hand side. But it's too wiggly in some sense, right? You see what I mean? Like there's all these little like minor adjustments and changes. And what that's probably indicating is that it's overfitting to the data, especially kind of on the left and right hand edges where there's a lot of points kind of clustered around each other without too much of a change. It's chasing some of those. On the other hand, the support vector regression model looks really nice. It does a great job of capturing the curve we're looking for with a nice smoothness to it. So it picks up the smoothness in the data, and it's very accurate, more so than the other two. So it's a good illustration of how this support vector machine approach is really a useful one when you're dealing with data that you expect to have a highly nonlinear structure. Okay, so let's go back and I'll just recap that real quick, what I just said there. Okay, so observations. So Mars, so it has trouble with smoothness. And doesn't capture the structure of, for whatever reason, one part of the data, that part on the left-hand edge. Okay. As mentioned, RF is too, in some sense, wiggly. I don't know a better term to use to describe this, but that's what we see visually, right? There's too many kind of little adjustments and changes, and that's indicative of overfitting. There's too much sort of point chasing going on in the Random Forest one. But the support vector regression model, there's not really anything bad to say about it, right? So it captures the smoothness well. And it's quite accurate. Okay, so I think a good illustration of the advantage of the support vector machine approach. So with that in mind, let's conclude by talking about some advantages and disadvantages, something we always like to talk about when we're discussing advantages and disadvantages. Anytime we're talking about a machine learning model, it's worth discussing why is this a useful, what are its advantages, so why is it useful, and what are its disadvantages, why might we want to pick something else. So support vector machine advantages. And a lot of this is recapping observations that we've already made. Okay. So one nice thing about support vector machines is they directly attempt to maximize generalizability. So that means that they're basically set up to not overfit in some sense. Like the method itself theoretically is kind of designed to work against overfitting. They are always, although they're always guaranteed to have a globally optimal solution. Now, it doesn't mean we're going to achieve that solution, because we might not, of course, when it comes to training, we're going to have limitations on our computational runtime and how many different parameter values we can assess in a grid search and so on. But theoretically, this is they always will, and the reason why is because they're convex optimization problems. And you could prove this. I mean, this is like a theorem in optimization, in convex optimization theory, that such problems theoretically always do have a globally optimal solution, even if practically speaking, finding it may be hard. Okay. They're robust to outliers. So using a soft margin. And tuning the cost parameter. And as we've seen through examples, they adapt well to nonlinear relationships. In some sense, they're kind of ideal for dealing with, say, what you might call shallow nonlinear problems. So nonlinear relationships on relatively small data sets. For extremely large nonlinear relationships, you may want to consider neural networks instead, right? If you've got some enormous data set. So disadvantages? Well, as we've seen, the actual algorithm is only set up for binary classification, so they require additional special procedures for multinomial classification and regression. Support vector machines only produce class predictions not class probabilities. So they don't tell us a probability that a point lands in a particular class. It just tells us, it just predicts what class it's in based on the separation, right, from the hyperplane. And then even in the multinomial class, these 1 versus 1 or 1 versus all set specifications. Okay. Now, it's possible to obtain these, but they require much more advanced techniques. So this is discussed a little bit in the textbook if you're interested, but it's fairly technical stuff. And a general problem with them is that support vector machines can be slow to train on what we call tall data. And tall data means the number of data points n is much larger than the number of features p. So if you think about it, if you think of your spreadsheet, it looks tall in the sense that, right, if it were a building, it would be fairly narrow at its base and very tall at its height, right? So a lot of rows and not that many columns in comparison. And this is basically because if you think about the convex optimization problem you're solving, essentially what you have to do, if you go back and look at it, right, the subject to part has a condition where you're for every value n in the data set, right, or is every value I, like for each ith data point, you have to have some sort of estimate on the well, you need essentially the hyperplane value. So the parameters that you're optimizing the parameters. I'm not saying this very well, but you're optimizing over beta 0, beta 1 through beta p. And you need to essentially have your condition, whether it's the hard condition or the soft condition that included the fudge factor psi sub I. You need to check that essentially. You need to be verifying that those are satisfied for every data point, right? The ith data point for all data points up to n. So it's basically the reason it's slow to train on tall data is because the convex optimization algorithm is slow in that sense, in terms of how many checks are required, how many things you have to verify that you're actually optimizing as you optimize. So that's the issue. It's kind of just a technical mathematical thing. Okay. All right. So that is all I wanted to go over. So we're at the end of the lecture material. And quiz 6 is next Friday, so not tomorrow, a week from tomorrow, on chapter 14. If you have any questions while you're getting ready for that, let me know. And if you need any extensions on any of the assignments, if there's anything you haven't gotten submitted yet, let me know. I'm happy to do that. And I'll be sending out some reminders and just things about the project and so on. As I mentioned at the start of class, we'll bump the due date. The formal due date will be Monday, the 19th of December, rather than Friday. So no, Monday the 20th, I guess. And yeah, and I think that'll probably end up having to be a hard due date because I think grades are due on the 22nd. And so it'd be nice to have a whole day to actually grade them the Tuesday, something like that. If you do want to get it in sooner, there's no problem with that. And so just one last reminder, no class next week. Work on your projects, finish up any assignments, and I'll be in touch.